Hello AP Chemistry and welcome to 15.5 and 15.6 where we're going to talk about all the math that goes with K. All right, so let's go ahead and start some problem solving. An aqueous solution of acetic acid is found to have the following equilibrium concentrations. So there is the key word, right? Equilibrium concentrations, meaning that these are the concentrations at equilibrium, right? And it gives us some concentrations and asks us to calculate Kc. So first, what should we do? Right, let's write us an expression, right? Kc is equal to our acetate ion raised to its coefficient and my hydronium raised to its coefficient all over our acids raised to its coefficient, right? And so all we've got to do is plug in our equilibrium concentrations, right? This one is that simple. So it would just be this times that over that. Every once in a while, it is that simple. And then we would just solve, and that would give us our Kc, right? Okay, so now we move on to the next problem, which is a little bit more thoughtful. So it says sulfur trioxide decomposes at high temperature in a sealed container. Initially, keyword there, initially, we have SO3 with a partial pressure of 0.5. At equilibrium, SO3 has a partial pressure of 0.2. We would like to calculate Kp, right? So first, let's go ahead. Well, first let's talk about how this problem is different from the previous one, right? So here, in this problem, we had all of the equilibrium concentrations. So we just plug the equilibrium concentrations into K, right? Here, we only have one equilibrium concentration, meaning we don't have enough information to plug into K. So step one is find the equilibrium concentrations, right? Because I need those to plug into K. So how do we find the equilibrium concentrations? Ding, 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 a Rice table, right? So let's go ahead and put that together, right? So we have, first we have our R part, which is our reaction. So we have our SO3, gives us 2 SO2 and some O2, right? And then we have our initial, which is 0.5 atmospheres. And if we only have that, that means we have 0 of each of these, right? That's what that means, right? Change, right, is dictated by our stoichiometry, meaning that we lose 2 times some number of that. We gain 2 times some of that. We gain 1 times some of that. Yes, as in we produce some and we lose some, right? We produce product, we lose some reactant, all right? Now, the question also tells us, though, that we have 0.2 atmospheres, right? Is our final here, right? So, and this is going to be plus 2x, and this is going to be x, right? Which means that we can, dun, 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 solve for x, right? This gives us the ability to solve for x, right? So I know that 0.5 minus 2x is equal to 0.2, right? And so we can solve for x. And x equals 0.15, right? And this is atmospheres, right? So then what that means is I can plug that into all of my other things, right? So that means this is actually going to be 0.3 atmospheres. And this is 0.15 atmospheres. And then I can take all of that and plug it into my Kp, right? So my Kp, let's go ahead and write down what the expression is, right? So Kp is partial pressure of SO2 squared, partial pressure of O2, and partial pressure of SO3, also squared, right? And so we'll just plug in our pieces. Kp is equal to 0.3 squared, 0.15 over 0.2 squared, and solve for Kp. Yes? All right. So, what happens if the system is not at equilibrium, right? And this is where Q comes in, where Q is our reaction quotient. Reaction quotient, right? And what that means is that's the exact same equation as K, right? So this is going to be my products raised to their coefficients over reactants raised to their coefficients. And it's the exact same thing. But this can be at any time, right? Where in a K expression, we are limited to equilibrium, right? Here, for a Q, we can plug in concentrations or pressures at any point in time, and that's going to give us a point of reference for what direction the reaction will move from that point, right? So when K and Q are the same, right, clearly we are at equilibrium, right? If Q is less than K, right, so let's think about what that means, right? If Q is less than K, right, what that means is there is too much reactant. Yes, my denominator is bigger than it ought to be. Or we could say my numerator is smaller than it ought to be, which means the reaction will go forward to produce product and consume reactant such that it will reach K, right? If my Q is greater than K, right, perspectives include, there is too much product, there is not enough reactant, so the reaction will then go in the reverse direction to produce reactant and consume product so that Q eventually equals K. Yes? All right. This is important because it gives us a simple quantitative way to assess where a reaction is right now and where it is heading, right? So if we read this problem, it says at 1000 Kelvin, the value of Kp is this. So note that we are given a Kp. The value, calculate Qp and predict the direction that the reaction will proceed, right? So note that kind of like how in sophomore year I said, I'm not going to ask you this, baby step question. This is the same thing where the question could omit this part, right? Calculate Qp and just ask you, predict the direction. And you should be like, that means this is a Q versus K problem, right? Anything about predict the direction or what will happen to the concentration of products, what will happen to the concentrations of reactants or the masses or the amounts present or what will happen to the pressure in the vessel, right? All of those, right, assuming we're talking about a chemical reaction, are really Q versus K questions, right? Where is the reaction right now and where is it going, right? So, calculate Qp. So first, let's start with a Q expression, right? So Q is going to be equal to PSO2 squared times PO2 over PSO3 also squared. And we'll plug in our what we have, right? So these are initials, right? So let's go ahead and plug those in. And this says 0.41 squared times 2.5 squared. Oh, not squared. Over 0.16 squared, right? So what we do is we would go ahead and solve for that, right? And we would get that Q is equal to 16. And then we would look at Q versus K, right? So if Q is equal to 16 and K is equal to 0.338, what that means, right, is this value is too big, right? That means ways to look at that would see that there is too much product present. So what we're going to do is consume product and produce reactant, right? Consume product and then produce reactant, or let's say make reactant, which means it's going to go in this direction. Yes, does that make sense, right? That's what the reaction is going to do, right? So that way it heads toward K, right? Because reactions will move toward whatever their equilibrium is. All right. Next up, at 500 Kelvin, the reaction blah has a Kp of that. In an equilibrium mixture at 500 Kelvin, the partial pressure of this is that, and this is that. What is the partial pressure of Cl2? So now we have a Kp, we have some equilibrium stuff, but not the other one, right? So what might we do here? Right. So we don't have an initial for the Cl2, right? So we can't do it that way. But really all this is just an algebra problem where we solve for our x, right? So let's start with a Kp expression. So Kp, again, is equal to PCl3 times PCl2 over PCl5, right? And we're going to plug in what we have, right? So we have 0.497 is equal to PCl3, which is 0.350, times my PCl2 over 0.860, right? And we would just solve for my PCl2, right? So that is something that you have been doing since like 7th grade, and you can do that, right? Next one says, for the equilibrium blah, the Kp is this. A gas cylinder is charged with, so that's what we start with, right? Initial pressure of this at PCl5. And I would like to know everybody's equilibrium pressure, right? So which means that all I have is an initial and a Kp, and I would like to know the equilibrium pressures. If I want to do that, where should I start? Right. Let's do a Rice table, right? If there's something we can't figure out, there's not something that's a straightforward algebra problem, right? That means we need to set up a Rice table. So what we're going to do is let's get that going, right? So we've got PCl5, PCl3, and Cl2, and we have an initial of 1.66. We got none of this because that's what that means, right? And we're going to lose some, make some, right? And we have 1.66 minus x, and x, right? And all of this goes into a Kp expression, right? So I don't know why I tried to squish all this in here like that. Let's move this off to the side a little bit. And then we're going to do the next part, right? Which says that we are going to take this and plug it into our Kp, right? So Kp, and we already have the expression up here, right? So what we're going to do is set it up. 0.497 is equal to, right, x times x over 1.66 minus x, right? So that's what that looks like, and now we have to solve for x in order to figure out our answers, right? You might look at them and be like, ooh, that's a mess. But then you would remember, oh, duh, I learned the quadratic equation a million years ago. I can do this, right? Also, you guys have those TI Nspire calculators with a solve function. Note that I don't recommend using it in general, right? Because we have to have the ability to quickly manipulate basic calculations in our head, right? That's going to help us make sure we do math correctly, right? This, though, this is beyond what a normal do it in your head calculation would be, right? And so this is the one time I would recommend using the solve function on your calculator, and let's take a look at what that would look like. Okay, so first you're going to find the menu button. And under menu, you are going to, not that one, you're going to click number 3, algebra solve. Now, when you get to the solve, you'll see this, and then we just have to enter our problem, right? And so you'll see the problem in the upper right hand or upper left hand corner, right? Where we're just going to type it in, right? So 0.497 equals x, well, x times x or x squared, however you want to do that, right? Divided by our denominator, which is our 1.66 minus x, making sure that appropriate phrases are in parentheses as needed. And if you're not sure, if you don't remember order of operations very well, use more parentheses than you ought to, and that would be a good choice, right? And then when we stop and look at our choices, right, because it's a quadratic, it's going to spit out 2 answers. We're going to look at those 2 answers and pick the one that makes sense. Only one of them is going to actually work in the context of the problem, right? Meaning that 1.66 minus x can't be a negative number, right? We can't have a negative concentration. So only one of those numbers is going to make sense. Yes? All right. And then we solve for x and solve for the rest of our pieces. So 0.693 is x, which is the concentration of PCl3 and Cl2. And 1.66 minus x is the concentration of the reactant that remains. All right, thank you for listening. Be good, and I will see you soon for the rest of Chapter 15. All right, be good. Bye.